Okay, so that's probably way more deep than we needed to get about this topic, but I really like it, so deal with it. Let's talk about energy changes in chemical reactions. And this is an area known as thermochemistry. Could anybody describe to me what thermochemistry is, if you had to guess? Yeah, heat. Heat dealing with what? So heat of what? Study of heat and energy and what? Yeah, chemical reactions. Okay, so have you ever wondered, like, how many people look at the ingredients label on like the food you eat? Anybody do that? I stare at them all the time. Any calorie counters here? Anybody like stare at the numbers that are on there and log it on their phone or whatever? I do that because I care way too much about it. Where do they get those calories from? Where do they figure that stuff out? How do they know that? Yeah. Yeah, basically, they burn it and they generate heat, and they measure the heat that's coming off, or they combust it in something called a bomb calorimeter. So thermochemists tend to deal with that area. They look at the flow of energy, and this can be really important. One, in terms of food. Two, in terms of large industrial processes. If you're generating a lot of heat, you can actually melt an entire plant. This happens way more than it should. Or if you're thinking about biological systems, knowing if you want to denature a protein, if you want the protein to fold properly or improperly, is going to really heavily depend on the thermodynamics of that system, right? So we have we have the word heat, but we really haven't defined it yet. Heat. We're going to give it the symbol Q. Anybody have an idea of what heat is? Again, that's another one where we all have an intuitive idea. We've all felt heat before in our lives, right? Put your hand near a stove, you feel the warmth coming off of it. So how are we going to define heat? Any ideas? Or any buzzwords?
Couldn't it be the amount of kinetic energy?
We're not going to say kinetic energy. We're going to say thermal energy. But yeah, so it's the amount of thermal energy and what are we keeping track of? How do we know? It's the amount of thermal energy. What happens with that thermal energy? Yeah. Yeah, it's being transferred between two bodies, right? Absorb or release. Yeah. So it's the amount of thermal energy transferred between two bodies. Which are at two different states. Don't want to violate the 0th law of thermodynamics. Different states. Okay. So again, we're going to have some more boring definitions, but these definitions are very important. I didn't understand how important the linguistics was behind thermodynamics until I started taking way too many advanced classes in it. Okay, so whenever we're talking about something in thermodynamics, we define a point as a system and something else as the surroundings. So let's talk about that. We have the system, one of the parts. So the system is the part of the universe that we're trying to study, we're trying to understand. the part of the universe we are interested in. It's the system we're trying to study. That's what we want to know about. Therefore, what are the surroundings then? Yeah.
Everything that's not in the system?
Yeah, exactly. Everything else besides the system. So the rest of the universe. Outside of the system. So that leads us to a handful of different types of systems we can talk about. Okay. Am I okay to erase this bit here? So there are three systems that we tend to discuss. We have open systems. We have closed systems. And we have isolated systems. Okay. In an open system, we have our little box. This little box is actually the system that we're interested in. And then everything on the outside is the surroundings. So let's say I have a cup. I have a cup of ice water. And I set it down and it's sitting in the sun. What's going to happen to that cup of the ice water? Yeah, the ice is going to melt. Let's say I leave it there for like 3 days. That's going to evaporate. It's going to leave. That's an example of an open system. So what things are coming and going in the system? Energy. Yep. So we have, in this case, we're gonna say heat. We're gonna keep track of things in terms of heat right now. So can heat between the system and the surroundings, can that be transferred? Yeah. What about mass? Can that be transferred? Yeah. So if you think the top of the glass is open, things can move in and out. Okay. So let's say I have a lid, like I have a I don't know, one of those crummy cups, like plastic cups that I see people around with, and I cap it. That's an example of a closed system. So in a closed system, let's say I'm considering heat. We have our cup with a lid on top of it. Can heat still flow in and out of this system? Does it? That bottle of water over there that Victoria has. If you let it sit in a really warm room, what's going to happen to the temperature of the liquid on the inside? Yeah, it'll heat up, right? So can heat transfer? Yeah. Heat can transfer. What about mass, though? Can that transfer? Nope, can't go through. Now, for an isolated system, what could you guess about both of these? We have heat and we have mass. What's going to happen in an isolated system? What's that? Yeah, there's no transfer of either of them. Can we ever actually have an isolated system? Like, can we create one? We do our best. Like, could you give me an example of something that contains a hot liquid that doesn't like to let the liquid move out of it or give off heat? Yeah. Yeah, thermos is a perfect example of where we're trying to create an isolated system. We haven't been able to make an isolated system. We think the universe is isolated, and that causes a lot of problems and a lot of hardship for people later on. But we can't ever actually make a truly isolated system, because even in that thermos, let's say we let that thermos sit for like a day. The temperature is not going to really change much, right? If it's a really good one, it's like one of those really expensive Yeti thermoses. What about if we let it sit for 1,000,000 years? Eventually that liquid's going to cool down to wherever it is, right? Yeah. A closed system, let's say a cup with a lid. And we said an example for an isolated system. What do we say? Thermos, right? From us, like that. Oh, thermos. All right, and then this one we just said just a cup, right? Okay, that's going to become very important later on when we describe some of these other things. All right, one more set of linguistics that we have to cover. Exothermic and endothermic, where we're talking about heat transfers. When a process is exothermic, is that heat being given off or heat being taken in? Yep, heat is given off. So any process which gives off heat. So in that case, what is giving off energy? The system or the surroundings? Yeah, the system gives heat, or excuse me, yeah, we'll put gives heat to surroundings. Okay, what about endothermic? What can you tell me about that? Yeah, go for it. Yep, any process which absorbs heat. Where is energy flowing to and from? Surrounding, yep. Surroundings to system. Energy from surroundings to system. Okay, so now let's look at an example. Or actually, I'm going to ask you a question. You have a cup of ice water. You have that cup of ice water and you hold on to it. Are your hands going to feel cold or hot? Yeah, your hands will feel cold. Hold it, and your hands feel cold. If the system is considered to be the water, is this an endo or an exothermic process? exothermic or endothermic? It's kind of a 50-50 shot right now, right? Okay. If you think this process is exothermic, I want you to raise your hand. One. Sure. If you think this process is endothermic, raise your hand. Okay. Why'd you raise your hand? Right, and that's why it feels cold, right? Your hands feel cold. Where's the energy flowing from? Yeah, it's coming from your hands. That's why they feel cold, right? For some reason, most other classes